In this video, we're going to see how we can solve differential equations by using power series. Power series is an incredibly powerful tool in mathematics, and indeed, it's going to make a large class of differential equations solvable that we didn't know how to do by other methods. Here's the idea. I want to begin with perhaps the simplest differential equation I know, that y prime is equal to y. Now, as we know, this has the solution y equal to c to the x, but in this video, we're going to use a very different approach, which is power series. That is, let me suppose a solution looks like this big mess, a sum from n equal to 0 to infinity of cn times x to the n. This is a power series. It's a function of x in the sense that if you give different values of x, you get different values out of it. But the big question is a question of convergence. You're taking an infinite sum of things. Does that add up to a finite number, or does it diverge? So what I'm going to do right now is make an assumption that I haven't justified, but an assumption right now that does have a convergent power series on some interval I. Now, before we jump into solving this differential equation, I want to review just a couple important facts about series. The first thing I want to talk about is how we use series to approximate functions. My claim here is that this is the power series expansion for e to the x about x equal to 0. And if I look at this sum, it's, well, a sort of infinite polynomial, if you wish. But if I only take the very first term, if I only take y equal to 1, then that's the graph of just a straight line. You'll notice that y equal to 1 is actually an excellent approximation to e to the x at the value of x equal to 0, but far away from x equal to 0 is a kind of terrible approximation. 1 plus x, if I add the next term, is actually a better approximation. Now I get another straight line, but because it's now tangent to e to the x, it's not only a good approximation at 0, it's sort of an okay approximation around 0. If I add now the x squared over 2 terms, so I get quadratic, now you're starting to see that this quadratic lines up really nicely with e to the x. I can add a cubic term, it now lines up even better. I can add a quartic term, it adds up better yet again. So here's the point. If I put all of those polynomials up here, as I have more and more terms in this series expansion, I get a better and better approximation for e to the x. It's in this sense that we think that e to the x and this infinite series are the same thing because they converge to be the same thing as the number of terms you take goes to infinity. The next thing I want to remind you of is the series expansions for a lot of the standard functions like e to the x, sine, cos, and the geometric series, which adds up to 1 over 1 minus x. So these are all known series, and we're going to use them as we solve differential equations. Now, the way these came about were that they were Taylor series centered at the value of 0, or sometimes called Maclaurin series. Either way, they came from this formula highlighted at the bottom. Namely, if you can compute a whole bunch of derivatives and see some nice pattern, you can get the series out of it from there. Alright, so let's return to the differential equation that we were studying and the assumption that it can be written as this convergent power series. The first thing I want to do to that assumption is I want to take its derivative. Indeed, we have a theorem that says if you have a series which is convergent on some particular interval, you can take what we call the term-by-term derivative of it, which is what I've done here. So the sum stays out the front, and then for each term I take that derivative, x to the n goes to n x to the n minus 1. When you take this term-by-term derivative, you get that it's also convergent on the interval I. I'm going to do one little trick here. Notice that there's actually a 0 on the bottom, n equal to 0. But if you plugged in n equal to 0, there's also an n in the expression here, cn times n. So when you plug in n equal to 0, you just get a 0th term. So having n equal to 0 doesn't do anything. So I'm just going to replace it with the value of 1 instead. You'll see why in a moment. Nevertheless, I have a y. I have a y prime. The claim is that y and y prime are equal, so let me just plug those two things equal to each other. I have two series. I want to compare them. I want to compare the coefficients, but I unfortunately can't quite do that. The reason is that one is coefficients times x to the n, but the other is x to the n minus 1. That is, they're not written with the same index. But that's okay. We can shift index on series like these. For example, we can send n to n plus 1. This is just rewriting our sort of indexing variable that keeps track of this series. So we're allowed to do this kind of shift. So if I do that, several things happen. Instead of starting at n equal to 1, when you shift n to be n plus 1, that's now starting in the new index at n equal to 0. Instead of cn, it's cn plus 1. Instead of n, it's n plus 1. And now the good part, which is the exponent, the x to the n minus 1, turns into an x to the n. And now I do have like terms. They are the same on the left as it is on the right. They're coefficients of x to the n. Okay, so clearing some space, I'm now going to use an identity theorem. And it says that if I have x to the n on both sides, then if I look at those coefficients, the things in front of the x to the n, they must be the same. And this gives me the equation that Cn plus 1 times n plus 1 has to be equal to Cn. It is often convenient to rearrange this equation and say that Cn plus 1 is Cn over n plus 1. What I have here is something called a recurrence relation. It tells me what the n plus 1th coefficient is in terms of the nth coefficient. For example, let me assume that C0 is just some constant. I'm not going to try to solve it, it's just a constant. C1 would be like plugging n equal to 0 into this formula. In other words, what the C1 would just be the value of C0. In other words, C0 on the top and 0 plus 1 on the bottom. Okay, great. So now I figured out the C1. What about the C2? Well, now C2 is like using n equal to 1. So it's the value of C1 on the top, which we just saw was the same as C0. And then divided by 1 plus 1 is 2 on the bottom. Okay, so this is C0 divided by 2. What about C3? Well, it would be that thing, C0 divided by 2, but then divided by 3 on the bottom. What about C4? Well, it would be C3 divided by 4, and so on. So what this recurrence relation is doing is it's starting with C0 and then dividing it by 1, then 2, then 3, then 4, then 5, then 6, and so forth. And so generally, I'm going to say that Cn, the nth term, is just going to be the initial C0, but divided by n factorial. For example, C5, say, is C0 divided by 5 times 4 times 3 times 2 times 1, which is 120. Okay, so we knew what the general expression for y was supposed to be, but now we solve for the Cn's. We was put this together and say, I've got my general solution, Cn x to the n, and I know that the Cn is C0 divided by n factorial, and so my final answer is thus y is a constant times the sum of n equal to 0 up to infinity, x to the n over n factorial. Now this is precisely what we saw the expansion of. That's just the expansion of e to the x. It's a constant times e to the x. And so we have recovered the same solution that we had at the very beginning. It's worth noting here that when we tried to solve for the Cn, we determined all the Cn's in terms of C0, but we never determined what the C0 itself was. If I had specified an initial condition, then you could have used that, plugged it in, and then gotten the value of C0. By the way, mathematicians often will define e to the x in different ways. It's not incorrect to define e to the x as the power series, like what is this function e to the x? The answer is it is that power series. It's also not incorrect to say that e to the x is the solution to the differential equation y prime equal to y. Perhaps with the initial condition that y of 0 is equal to 1, which will impose that the constant C0 is just equal to the value of 1. Nevertheless, these competing definitions are aligned in this particular methodology. The final thing I want to talk about is when does a series like this converge? Now, e to the x is known to converge everywhere, but how do we know that? There is a theorem that I will remind you about from back in first year calculus called the ratio test. And it says that if you have some series, some sum of an's now, where in our case we're thinking that the an's are probably a constant times an x to the n, but nevertheless just some series in general, then what you do is you look at the limit of the ratio of successive terms, an plus 1 over an. You get a couple different possibilities. That limit might be less than 1. That limit might be less than 1, in which case the test tells you it converges. That limit might be greater than 1, in which case the test tells you it diverges, or that limit might be equal to 1, in which case unfortunately the test fails or is inconclusive and you're going to have to do some other types of analysis. So let's see this for our specific example of e to the x. So if I take that ratio, I'm taking a limit as n goes to infinity. On the top, a n plus 1th term looks like, well, the constant, x to the n plus 1 over n plus 1 factorial. That's the an plus 1 on the top. On the bottom, very similar, there's the C0, there's the x to the n, and the n factorial. Now, a lot about this messy expression cancels, the C0's cancel. The x to the n plus 1 on the top and the x to the n on the bottom, they mainly cancel and leave you just 1x. Likewise for the factorials, if you have n plus 1 factorial on the bottom and n factorial on the top, almost all of n plus 1 cancels from the n factorial and just leaves you with n plus 1 on the bottom. This expression that we have is going to be 0 because no matter what your value of x is, say a billion, then you can always find values of n large enough to take x divided by n plus 1 to as small as you might wish. So this limit is 0, and thus, by the ratio test, it converges for all values of x.